Sorry, I can't hear you. I've got my new noise-cancelling headphones. You know that, and your camera. But I'm just going to assume that you want to know how these noise-cancelling headphones work. Well, to explain that, we're going to introduce you to the world of interference. So, in case you've never seen a wave before, that's what they look like. This simulation shows that the yellow wave and the blue wave are combining to form the green wave. How does that work? Well, right now, the yellow wave and the blue wave are what we call in phase. And that means that where there is a peak on the yellow wave, at the same place and the same time, there is a peak on the blue wave. And they combine to give you a bigger wave, or rather, a wave with a larger amplitude. If these two amplitudes were the same, that amplitude would be double those amplitudes. This is called constructive interference. Now, what do you think might happen if these waves were out of phase? Well, as you might expect, out of phase is the opposite. It's when the peak of a yellow wave is at the same place at the same time as a trough from the blue wave. Provided these two amplitudes are the same, they will combine together to give you no wave at all. And that's called destructive interference. And it's how these noise-cancelling headphones work. So when you are listening to music and wanting to be very antisocial by not listening to anybody outside, shut up! On these. What they do is they record the noise from the outside, like other conversations happening, and they play that noise back in to your ear, which you might think completely defeats the point. But they play that noise back in exactly out of phase with the original noise. So this is the original noise, that's the playback noise, and overall you hear very little. Now, it takes a little bit of time for the electronics to kick in, so this works well for continuous noises like the engine of a car. It wouldn't work well if somebody was just to come up to you and go, "Bah!" Okay? Just so you know. I'm going to ask you to make a prediction. I have two slits on this sheet of card. And I'm going to pour some sand through the slits. Now, what do you think you are going to see on the tray below? Now, you might think that what you'd see would be two ridges of sand, right? Where the gaps were. And you'd be absolutely right. That's exactly what you see. Okay? So you've got one ridge here, where there was one gap, and one ridge there, where there was another gap. Go you. Now, if I was therefore to do the same thing, but with light, or a laser light, and shine that through two slits, you'd expect to see a similar thing, right? Except bright spots, rather than sandy ridges. Let's do it then. I'm going to shine a laser beam, which is at the back of the classroom, through a double slit. Now, you can't really see this on camera, but right there are two incredibly narrow slits that I'm going to shine my laser beam through. And let's find out what happens. Make the classroom nice and dark. Particularly hard to see. I think we're okay. We're okay, it's fine, just ignore that. And I'm going to turn on the laser light now. But it might be quite hard to see what is on the screen. So let me make that a little bit clearer for you. Voila. What the heck is going on? I'm shining a laser beam through two slits, and I'm not seeing two bright spots. I'm seeing what we call an interference pattern. How the heck can this be happening? We've got a bright spot in the middle, and then a dark gap, followed by another bright spot, and so on. There must be an explanation for this, and I probably wouldn't be doing this video if there wasn't. So let's find out. What is going on? To explain, I'm going to have to talk about constructive and destructive interference again. If you imagine that when I shine my laser beam through this double slit, I'm effectively creating two different light sources, right? That's coming from slit 1, that's coming from slit 2. And as long as there's no difference in the length from each of these slits to the screen, there's no path difference, then the peaks from these waves are going to line up right along until you hit the screen. That's constructive interference, bright spot. But if you look along the screen, like we did, you see a dark spot. What's going on there? Well, in this case, the second light source is now having to travel a little bit further to get to the screen. In fact, in this instance, it's having to travel exactly half a wavelength further. And that means that these waves become out of phase. You can see the peaks are lining up with the troughs. And so you get destructive interference and a dark spot. So how on earth do you get another bright spot again? Well, this is still having to travel further, but now it's having to travel a whole wavelength further. If you will, it's now so out of phase, it's back in phase again. It would be like you turning up 24 hours late to registration, right? You'd actually be on time, but for the next day. And I wouldn't recommend that you do that. So it's the same here. These waves are now back in phase again. The peaks line up with the peaks. You get constructive interference and a nice bright spot. Okay? So I've shown you clearly in this video that light definitely behaves like a wave. Well, you know how you behave slightly differently depending on the scenario? Like when you're with your class teacher, you're obviously incredibly driven and motivated. When you're with your parents, you try and communicate with as few syllables as you can possibly manage. And I presume, when you're with your friends, you're just chatting about how awesome physics is the whole time. Well, light is kind of the same. It behaves differently depending on how you measure it. But to explain that more fully, I'm going to have to do another video called the photoelectric effect. So watch that and you'll find out that light has a dark side. That was weird.